probably the bulwark of a lot of data analysis, which is the data frame. And I'm guessing you guys are familiar with the data frame and also with sort of the tidy data format. That's kind of true? Yeah, pretty straightforward. Spreadsheet is kind of what we're talking about here. The tidy format means that, and this is just a table of electric vehicle charging locations across North Carolina. And so each row is its own feature, its own charging site. And then each column represents an attribute or a measurement of that feature. So again, this is pure data analytics. And then we have lots of tools to play with these things. But what I want to focus on is, one is, well, this data set happens to have these two columns, latitude and longitude. And so that means that we can extract a location from them. And so the first step into geospatial analysis is converting these attributes into a new data type, the geometry data type. And this is, you'll see the coordinates are there, but the computer and the software, they recognize this as a different entity, and this kind of opens up the door to a whole host of new spatial analysis. And that's what I want to drill into now. But before we do that, let's take a final look at this. So they don't necessarily have to be points. But they can be points, lines, or polygons. And between those three entities, we can pretty much represent anything we want as a map. And here's just a quick map of Duke's Quad focusing on the chapel. And you'll see, you can kind of recognize that on here, we have points or single locations. We have lines, trails, et cetera. And we have polygons, which are the forest boundaries or building footprints there. So points, lines, and polygons is kind of where it all starts with one particular type of geospatial analysis. And from a data perspective, these are stored in your data frame. These geometry objects are stored as coordinate pairs. So the easiest one is just going to be your single XY coordinate, a point. And now line is just a series or a vector of these coordinate points with a sequence, again, just defined by every time the line takes a significant bend, we put a vertex in there and establish that as a point, and the computer knows to draw these together. And then a polygon is the same thing as a line, a series of points, except for the last point overlaps the first point, and the computer knows to close that. And now we have a polygon. We can have adjacent polygons, and once we have these geometric features, we can do a lot with them. First of all, we have new properties. A line has length, a polygon has perimeter and area, so we can start to do new calculations. Now there's this other level of attributes that they have, something we call topology, which allows us, or allows the computer, I should say, because I'm too lazy to do this, is we'll have this line segment. Let me get my little laser pointer here. We'll have this line segment here that is shared between two polygons, and we can do special things with that. We can remove it. We can decide what's on the left or right side of it. So all kinds of things with it. So again, just this simple geometric feature made up of these coordinate pairs. Now we're getting to start to do some cool stuff. First of all, we can map it. And this is all covered under what we spatial analysis call the vector data model, because we have vectors of geometries. Before I move into what the fun things we can do with it, one important aspect of all this is that those coordinates that are listed in these geometric features are all referenced to a location on the Earth. Latitude and longitude is the most common way to do it. There's a whole lot of different ways of doing it. I'm not going to go down that rabbit hole. That would take a long time and get confusing. So we'll just stick with latitude and longitude. And you can see I'm just pointing to one feature here. And here's its longitude, 79.18 degrees west of Greenwich, and then 35.73 degrees north of the equator. So that's that point. So all these features has those points. And we can have line features as well as a sequence of points. And because these are all using latitude and longitude, all using the same referencing system that is tied to the Earth, we can plot these all on a map. And what the magical part about that is that allows us to take all kinds of disparate data sets that have these coordinates and work with them together. And that really is what spatial analysis is about, and what makes it a strength, especially in my field in the environment, because so many different data sets can be mapped, meaning that, okay, even though these are collected at different times by different people, different sensors, whatever, if they have a location on Earth, then we can associate them and we can do the spatial analysis. So geometries and georeferencing, that is sort of from a data perspective, that is the key to doing all these cool spatial analyses. So what are these spatial analyses? Well, I'm just going to go through a range from pretty straightforward to a bit complex with what we can do with these geometries. I think probably the simplest is things that you probably would be familiar with if you were doing standard data analytics on a data frame. So an example I want to do here that has to do with geometric calculations is a scenario, and this is tied to a class I taught a while ago, which looked at try to identify key places to put new electric vehicle chargers throughout North Carolina. And one of the sub-analyses there is, well, we'd like to identify vacant lots to put these in so that, you know, we don't want to have to displace anyone out of their home. So if we choose a vacant lot, we're good. So the little workflow here would be, first, of course, you have to find and obtain parcel data. And so I hope this isn't too small for you guys. So here is a data frame, and it is a spatial data frame, and we have 3 attributes and a geometry. So parcel ID, and then what kind of land cover designation that parcel has, a subdivision, which is a grouping variable, and then this last column here contains that geometry. So these are all polygons. So we obtain the parcel ID and then the parcel data set, and then just with standard data analytics practice, we do a query. Let's grab all these parcels. Let's subset all the ones that are tagged as vacant. And so that's just a standard query. All the rows where the land use begins with VAC, short for vacant. And then what we can do is we can group or aggregate these data by the subdivision. So this creates a new table. So we aggregate it. We do the group by command. And then we can calculate a summary statistic. So I'm calculating the sum of the area extracted from these geometries. And now I have a quick table of all the vacant area in each subdivision such that we can maybe concentrate on those that have a lot of vacant land. And because these are geometries and they're georeferenced, we can throw these up on a map and compare them with other data sets that are also georeferenced. So you can kind of see here in the yellow are these subdivisions that happen to have a lot of vacant land. So quick analysis dealing with one single data frame. Nothing too complex if you have a solid grounding in data analytics to visualize, other than now we're playing with geometries. So getting a little bit more sophisticated, but still based on analyses that are probably familiar to those of you who work a lot with data frames, is joining data. So on tables, you can join data on common attributes. If you have a data of counties and population and the data on counties and some sort of budget, you can join those based on the same county value. Well, we can do spatial joins using that geometry. And this allows us to combine all these disparate data sets to make a new data set where they're all together. So an example here would be maybe A, B, and C are parcels that we've identified as key spots to put in a vehicle charging or a solar farm array, something like that. And then we have another data set completely different of cities or counties or subdivisions, something else. And we can carry over the attribute of one data set to the other through the spatial join. So it just looks at, okay, where are you? In what city do you belong? We're going to add that attribute to your attribute table. Pretty straightforward analysis, but quite useful because now we have 2 disparate data sets that are unified as one. We can also do spatial selection, which is, okay, I want to identify features in one data frame based on geography relative to another data frame. And we can do something like find which city this particular charging location occurs, or we can get a little bit tricky and say, it doesn't have to be in it, but it has to be near it. So I'm going to specify a distance. Give me all the charging locations that occur within 300 meters of an existing power station. Or we can do all kinds of different, we call these spatial primitives of how to select features in one data set according to location and features of the other. So this is all pretty basic. So if you've done GIS before, you're probably right now going, oh, okay, all right. If you haven't, maybe this is a refresher, but maybe if your background is purely data science, you're kind of like, okay, this is kind of cool. So I leave that up to you. A few other just basic ideas to cover is we can modify those geometries that we have pretty easily. So if we have a set of points here, one thing we can do is, oh, I want to grow them. I want to buffer them. They don't have to be points. You can buffer a stream. I do a lot of stream buffering to figure out how much forest is near a stream. And a lot of these geospatial packages will say, okay, just buffer this. and it'll take those coordinates and do the math, and you have the distance or a shape around it. Or you can draw an envelope around all your original points. You can find the centroid, sort of the center of gravity of all your points, or you can draw something called a convex hull, which is just sort of the minimum polygon around a set of points. Each of these, you may or may not be thinking of specific applications, but this is all easy to do with GIS. Other things that are pretty fundamental to geospatial analysis. Again, we have two data frames now, or two sets of features, spatial features. We can do the set theory based on geography here, computing the intersection. Maybe here is one of our vacant lots, and then this is a power station or something like that. We want to make sure we get the part of the vacant lot that is within a distance of a power station, things like that. So all pretty straightforward, but all now abilities we can do with our geospatial data. Now shifting it up a few notches, now I want to go to the other side and take a look at sort of the more complex analyses that we want to do. So one is, it's called linear referencing or network analyses, and this has to deal with line features. So anytime that you go to Google Maps and say, hey, you know, give me the shortest route from my house to RDU and tell me how long it's going to do, this is based just on looking at line features and attributes of those line features. So those line features, those sets of coordinates have an order. And things we can do is measure, okay, go along that line 12 kilometers, and where am I now? This example here is actually taken from a project I'm involved in right now, which is there are a lot of hog farms in Southeast North Carolina. Those hog farms produce biogas, and we want to see if it's cost effective to get that biogas to market. And to do that, we have to pipe it to the existing gas line infrastructure. So if you see the orange lines here, these are existing natural gas pipelines. If you kind of look carefully, you'll see there these blue dots of various sizes. These are swine lagoons that are generating methane. We're going to capture that methane, and the larger the blue dot, the more methane produced, the more hogs there. And then what we want to do is build this most efficient pipeline that we can to carry that to the existing framework. So we develop these optimal pipeline frameworks, and then we use these line features and some other software. So we're getting a little bit beyond data frames. We're introducing some new software analyses, but it just is tracing up all these lines here to compute the aggregate upstream or up pipe biogas. And now we have the volume of biogas that needs to be transported through each segment here, which is going to give us an idea of the diameter and the cost of the pipe. So the basis of a lot of calculations, but this again starts with a data frame we created of the pipe locations, and then we can do some pretty cool analyses there. Some other analyses that we can do with our spatial data frames is spatial interpolation. This might be applicable to a few of you who want to look at sort of the dispersion of air pollution or other things like that. So we're taking locations where we have measurements and predicting locations where we don't have measurements through various algorithms. And there's lots of them. They kind of come into two categories: deterministic, sort of what we call inverse distance weighting, or nearest neighbors. And just looking at the magnitude and distance away from known locations to measure unknown locations. And then we can also do geostatistical methods. Kriging is a popular one, where we measure spatial autocorrelation and do other statistics to come up with different surfaces. And we can get fancy. If you look carefully, you'll see there's these green lines we can introduce as barriers to sort of block things. So we can get really kind of interesting results from these things. But again, this starts with a geodata frame or spatial data frame, and we apply some analyses with that. You'll notice here that the output here is not it's a spatial data set, but it is not point, line, or polygon. This is a surface, and I'll come back and talk about surfaces a little bit later on. All right, and now this is sort of the cutting edge of both spatial analysis and data analytics. And this is where I think the super cool stuff is, of course, the product of getting powerful computers in the hands of the masses, the advances of a lot of spatial algorithms and data algorithms to come up with some pretty neat data exploration options here. So starting simple, and again, I apologize if this is too small, but just to get the gist of it, remember when I talked about we could calculate the centroid of features? Well, we can do a weighted centroid and again, I like to think of it as kind of a center of gravity. So the map here is California population density by counties. And then if you look carefully, you see a sort of a constellation of these blue circles. And that is the center of gravity of population weighted, of counties weighted by population. And the different colors represent different times. So that the darker it is, the more recent it is. And sort of really what this is showing through a simple analysis is that more people are, or sort of the mass of California population is moving southward just by this analysis. So it's pretty straightforward to calculate the median center, not all that interesting. We have a lot of access to these clustering algorithms. You're probably familiar with clustering data based on values. Well, we're clustering based on sort of spatial density. And this is a nifty way of data exploration, data mining. This again, sorry, small, but this is the San Francisco Bay Area. And these data, so we have point data dispersed throughout the Bay Area. And what we want to maybe do is let's look for clusters, not based on any property other than location. So look at just sort of clustering of data. Maybe there's some speckled points there. And we can cluster them across space, also across time. And then we can do things like, okay, now that we have clusters of data, are there different properties? So an example here could be maybe these are network outages or power outages over the last 5 years. And what we can see is find clusters of them and then ask questions like, you know, are there differences in why this cluster lost power versus this lost power, and generate more and more hypotheses that we can explore. So density-based clustering, set of tools and packages, we can do that pretty straightforward. And we can also do spatially modified statistical analyses. Maybe you've done some multivariate clustering on your own. What we can do here is constrain the location of that and sort of make these spatial clusters, weighting location differently as we want to other attribute factors. So this is Germany, political divisions in Germany, grouped on not only location, but other attributes, demographic attributes. I think this may be like family size and income, and it could be something else like political leanings or something like that. Any attributes that you want to sort of together, find if there are any spatial patterns, sort of force a spatial patterning, and the software is going to do it. It may not be great, so you're going to have to evaluate sort of the scores on how meaningful these categories are. But if they're meaningful, then you can sort of ask, hey, what's going on in this cluster versus this cluster? Why is that different? It's going to give you a box plot of the various attributes that you looked at here. So it's the start of an exploration. You can also identify, okay, here's your cluster, but inside this cluster, you're going to have some members that really don't fit, and then you can ask more questions of that. Similar to that, we can do hotspot analyses, which is you're going to use these statistical methods, and I'm not going to go too far into those methods, not here, to identify locally high and locally low values of whatever attribute you want to throw at it. So something could be power consumption. So maybe here in the red neighborhoods here have high peak power consumption here, or in the blue they have low. And then we can ask like, well, why is that? And what's going on here? And then again, within these high and low clusters, we can also identify outliers. And finally, just to give you another example, we can introduce time to get these sort of space-time exploration cubes, where it's similar to these hotspot analyses, but then we can slice it by time if we have the data to drive it, so that we can see places that have gone from hot to cold, that have remained hot, remained cold, across time and across space. So some pretty interesting visualizations. And again, these really all start with a spatial data frame, and then we just churn it away into these analyses. So quite a bit that we can do right there. I throw this little website here, and I'm going to give you these slides later on, but this website here, I feel it gives you a really good exploration. It has presentations, tutorials, other things if you want to take a deeper dive into any of these. All right. So data visualization, I could have spent a day doing all kinds of cool data visualizations that GIS offers you. You can imagine we have maps speak an international language without speaking a word. So it comes with a really powerful media. There's all kinds of dashboards. It's a huge growth field in the software now. data analytics as well. What I did want to do is do a quick share of this data set here, which is from one of your fellows, 𝐸𝐫𝐻-𝐵𝐻, who just got his PhD at the Nicholas School. And I think he was a fellow in this program. Anyway, he was one of my favorite students in some of my GIS classes. And what he did recently, there was those string of blackouts in Texas recently. And he got a hold of the data, which was just an Excel spreadsheet. And he turned it into geometries, and they had times. And what you're seeing here are the outage events across the state of Texas, shown by magnitude. I think that's the capacity reduction here in megawatts. Also tagged, the color is going to be the source of energy. And then it's just going through time. And so it gives you a really cool visualization of patterns in power outages according to power types across Texas. So again, GIS lends itself really well to visualization. And I don't think it actually took Edgar very long to generate this, but I think it's incredibly useful. There's a link here to more of the work, including all the code that Edgar used to do this. Zipping right along, maybe not all of this is sticking, but hopefully you're at least getting appreciation for the range of geospatial analysis. So we talked about the vector data model. Now we're going to switch gears and talk about this other data model, the raster data model, the product of those interpolations as well as other things. And what I want to do here is just point out that this too, so this deals with imagery, and I think you did some sort of image classification previously. But this is also not a novel data structure from anyone who deals with data analytics. So instead of a data frame, now we're going to deal with arrays. So we just take an image, just as probably have you seen before, and the image is made up of pixels. Just so happens that each of these pixels represents an area of land, and that's all there is to it, except for the fact, of course, that well, we have our rows and columns. So here's our familiar data matrix with rows and columns, and of course we can stack them as well. And at each row and column we have a value, and the value can be continuous as a set of numbers, or it can be discrete. Raster data works with both of those to show either phenomena like elevation or entities. This could just be a value of 1 or no data, discrete values. But the key here is that what we're dealing with, row and columns in sort of our analytic world, also reflect actual locations, again, latitude and longitude or other coordinate systems on the real world. And again, by making sure that these matrices are georeferenced, meaning that they're tied to locations on the globe, that allows us to take an image collected from one aspect over here, from another aspect or source or whatever, and now they can all talk to each other. And that's all GIS is, getting these things to talk to each other so that we can do all kinds of cool analyses here. So this is just showing, okay, we can just sort of drill down. All those things are at the same geographic location. So this is a land cover data set. This is an elevation data set. This is infrared, and this is visible light. We can take all those and we can ask questions of it. And that's kind of the gist of raster spatial analysis. So they come in a few flavors. Map algebra, which is just taking these matrices and just doing familiar matrix algebra, if you will. So local operations is just taking, taking a pixel at the same location among different stacks or images and doing analyses. So it can take 3 + 4 produces a new output 7. Now, because these are spatially important rasters, it actually makes sense to look at your cell at a specific row and column and looking at its neighbors, because it's this actual geographic neighbor. And so we can do what we call focal or neighborhood analyses to come up with new outputs here. So we're just taking the cell and its neighbors in the cardinal directions, north, south, east, west, adding them up, and then we get a new value for that cell. And I'm going to give you some powerful examples of that in action in a second. And we also have these zonal operations where we have 2 data sets. So this could be a discrete data set. So this could be a raster where each pixel is assigned a value based on which county it belongs to. So we have county A. Let me get my laser pointer here. We have county A and county B. And now we have another data set here. And this could be something like particulate matter loads or number of electric vehicles owned in that pixel. And now what we can do is, instead of summarize by some common attribute in the data frame, now we're summarizing by common location among a different raster data set. So we're grouping it by county here, even though they're in 2 different data sets here, and we can come up with a summary statistic. All right, so I'm going to come back and I'm going to focus on these focal operations. And now we're going to do the same thing. We're kind of, now we've covered some of the basics. Let's take a deep dive and look at some of the power that this enables us to do, even though, again, we're dealing with a simple data analysis object, the matrix. So a lot of the work I do is elevation based. So if you think about a matrix where every pixel is its height above sea level for that circle or that square of land, and we actually have those data for the entire terrestrial surface of the Earth. So we can do these analyses, and some of these may be appropriate for you, maybe not. But if we take elevation, first of all, we can make a cool little elevation map. But if we take the elevation and also compare it around compare it to the cells next to it, we can easily calculate the slope of that cell, sort of the steepness of decline, and the aspect, the face of that decline here. And together, slope and aspect, we can kind of merge these and create these cool looking hill shape maps. And they're not only cool looking, giving us sort of depth, they also can be very important for if you're looking at for solar farms, for example, here, because what this is doing is we provide an elevation data set, and then we also specify a light source in terms of how high it is above the horizon, its azimuth, and then in what direction relative to the cell. It could be south facing, southwest facing, or whatever. And then the product is going to be a value reflecting the illumination that that cell is going to get from the light source, which can be quite useful if well, I don't want to put my solar array on the north side of a steep mountain because it's not going to get much light. So again, this is just done by taking a matrix of elevation and applying some operations to it. And it's quite straightforward given the software that we have. We can also do viewshed analyses. So given this point and these elevation values, there's some more sophisticated algorithms to calculate what other cells in that matrix are actually visible from that location and which are blocked by cells that are higher. So some surface analyses, I think I'll speed it up. I can go in depth with hydrology analyses, really cool. But this is the principle here is another focal analysis, taking the elevation of a cell and trying to find, okay, of my 8 neighbors around me, which is the lowest? And if you put a bucket of water in my cell, its contents, if everything's simplified, is going to go into this cell, which is going to go into this cell, and so on. So we can actually we can trace the flow line of water all the way till it reaches an ocean cell, if we wanted to. And I have this link here that gives a super cool visualization on just that. And by the other mean, we can also look upstream and say, okay, what are all the other cells that flow into me? And now we can look at a drainage area, which is can be really helpful for modeling floods, rainfall events. And again, we start with just a simple matrix of elevation values. Right, I know I'm throwing a lot at you. I'm hoping you're caffeined up and it's soaking in a bit. One quick more analysis that we can do with our raster data, distance analyses, which can be quite helpful. Here what we have is we start with these little red dots here, and we just calculate for every cell in our matrix its distance away from its closest dot. And this can be quite useful for just how far away is this to the nearest X. We can modify that by saying, oh, not every distance is equal. It's going to be a lot harder for me to cross that freeway than just to go down a block and through the underpass. And so we can assign costs and do a cost weighted distance. Again, just applying some pretty straightforward algorithms. And it's going to give us a result of, okay, I can tell you not only how far that is in terms of cost units, but in which direction you're going to turn from every cell transition. And we can identify, okay, given all these centers here, these are the allocation areas, so that if you're in any cell in this sort of peach color here, your closest focal point is this dot here, and so on and so on. And what I use it for, and actually what was involved in that pipeline data set that we looked at, is it costs different amounts of money to put a pipeline through different land surfaces. and we have a data set that tells us that relative cost such that, oh yeah, it might be a longer pipe, but it's going to be cheaper overall to bend around here. And we can calculate that. So this is going to be the least cost path between these two colors here based on some sort of cost surface here. And then this again starts with two raster data sets or two matrices, one showing those locations and one of cost. And then we throw that into geospatial packages and we can calculate that least cost pathway. I was asked to do remote sensing data here, so we'll do this quickly. And this actually also isn't a big transition from any sort of data analytics. And this again, remotely sensed data, again, they're just matrices. What makes them special is that the values in each pixel was collected from a sensor that is a satellite, a plane. We have these balloons, we can have towers, ships, and so on, just taken from somewhere else. But what this is, again, what we often see with satellite images, or I think one of you is working with NAPE imagery, we have these sensors, and they're passive sensors, meaning that the values that are returned are reflections of sunlight. And what we often do is take sunlight, which spans the entire electromagnetic spectrum here, and we slice that such that, and this is, again, sorry, this is if this is very small to read, but so there's a satellite called Landsat 7 that's been circling the globe for a number of years now, and it doesn't look at the entire electromagnetic spectrum. It looks at these 8 slices of it. So it's taking a section like here's red light, blue light, green light, and then it's going to, for each of those little slices, it's going to return a matrix. And the value of the matrix is the amount of light reflected if you filtered out everything but, in this case, green light. So if you had these special glasses that filtered out everything but green light, you'd have, okay, this is really bright, I'm going to give that a high value. This is really dark, this gives you a low value. So that's one matrix, but we have a matrix for every slice of the magnetic spectrum. So now, okay, let's put on these glasses that only filter out everything but red light. And now, so we have a stack of rasters, and we can do really cool things with that. One is just looking at it. So instead of looking at what we're familiar with like a red, green, blue as red, green, blue. So we have those swaths of wavelengths from the satellite image, and we picture that on our computer as that, but we can actually say, okay, what if we make infrared red and make red blue and blue green? And it's like, that sounds confusing, but you may see satellite images that look like this, that are really red. And what we're doing there is like, wow, when you do that, the vegetation really pops. Now it's red, which doesn't make sense, but it's really visible. So we can actually just see the landscape in a whole new light, I guess physically or literally in a whole new light. And there are these standard algorithms that we know, like if you compare red light with infrared light, there's this standard ratio called normalized difference vegetation index, or NDVI, which you just take those bands, you do some band math, and the high values indicate really healthy vegetation because they reflect infrared and they absorb red. And so this is just taking those two swaths of reflectivity and comparing them and looking at agricultural fields like, wow, this is really good over here. My crops aren't doing so well over here. Let's go investigate. Other things we can do is a lot of these satellites, as I mentioned, have been circling the globe continuously for a number of years and visiting locations. This Landsat 7 visits the same location every 16 days. So we can collect the same brightness value across one or many of those spectral bands and do a sort of a time series analysis and say, okay, yeah, it looks like forest, still forest. All of a sudden, what's going on here? This is a little different. And then all of a sudden it's like, okay, something new is there. We're not getting the same pattern of reflectance over time. And that gives us an ability to look for change. Like, oh, well, I guess the forest has now been cut down and has now been cultivated. So change detection. We can do classification, similar to, I think, what you've talked about earlier, or probably what a lot of you are working on, because I think that's Kyle's wheelhouse. So for a long time, we would do pixel-based classification, which would just be taking the same pixel, the same row column of data geographically, and looking at the different reflectance values at that location to come up with these signatures and say, and we could train our data set, say, okay, here are locations I know that are forest. Now go find all the other pixels that look like this, or that look like water or ag fields. So we can do our pixel-based classification, and we have a number of different algorithms. Maximum likelihood is one of the more popular ones, but we can actually do genetic algorithms and neural networks to figure this out as well. And really, as you guys are probably aware, the new thing is to do object detection. So instead of just looking at single pixels across different spectra, now we're segmenting our image and we're looking for shapes across those little segments. And this screen grab here is from Dave Johnston, who works at the Marine Lab at the Nicholas School. And what he does is he uses drone. He has a whole fleet of drones. And those satellite images, they typically are like 30 meter by 30 meter pixels, so pretty big. With drones, of course, you can get much finer data. This is a 2.2 centimeter data flown over one of the Outer Banks Islands. And what Dave is looking at is oyster reefs. And it would be like, you could take a picture from your drone, and then, you know, the human eye is amazing at recognizing this. So you could hire an army of interns to look at this. There's going to be some issues there. But of course, what we're interested in is let's train the computer to do it. We got powerful computers. We got convolutional neural network technology. And that's exactly what Dave did, is he took these images with his drone and a sensor just taking visible light. So we have red, green, blue. And then he goes in and tells the computer, okay, this is what I'm looking for. Here's an oyster reef, here's an oyster reef, here's an oyster reef. They have a unique color signature. They have a unique shape and shadow. Go find all the other oyster reefs in this photo. And again, it's done just through typical image detection. It's going to look, you know, section by section across your image, score it against a library of other images, say, oh, well, this really looks like this pattern. The convolutional neural network is going to say, and then if you expand it, kind of looks like this, and all of a sudden we have this overall scoring. And then, okay, we've decided these are these oyster reefs. And of course, you go back and you train your data. So, okay, so we've gotten pretty wild here, right? Now we have these object detection, and if you probably started here, it's like, and you weren't too advanced in data analytics, you're like, wow, that must be really hard. It's like, well, of course there's challenges, but really, we're dealing with these matrices, and if we wrap up, we're dealing with the matrices of image data, or we're dealing with spatial data frames, and that's where it starts. And then from there, it's kind of understanding what the technology can do for you, and more of these libraries are out there for you to do it, but you can really pivot the knowledge that you're learning now or that you already have and become geospatial analysts without a whole lot of effort. Now, of course, there's a big fat star there because you know, we're teaching semester-long courses on the nuance of all this, but it shouldn't be anything you're scared of. All right, so quickly, where to go from here? So a quick roundup of the software that's out there for you. So ArcGIS Pro is kind of the Microsoft Office of GIS. It is proprietary. Most academic institutions have site licenses, and you have access to the data. The software. We have that here. This is a desktop software. This is an online cloud version, which you'll have access to, often through the site license, but you can get these personal accounts pretty easily. Getting more and more powerful, but not as powerful as desktop. QGIS is open source GIS package, not quite as powerful as ArcGIS and ArcGIS or ArcGIS Suite, but getting there. You can do a lot of the stuff using Python and R, and ArcGIS Pro and ArcGIS Online are very tied with Python. So that's useful, but R has packages that do a lot of this. Some of the other interesting things, so Google Earth Engine has both access to a vast library of remotely sensed data sets, as well as some other demographic data sets and other data sets. And it's all free, and you can do it at a huge scale, broad scale. So sometimes if you want to do something like, oh, my computer can do maybe this section, it's like, well, with Google Earth Engine, let's do it for all of Mexico. Why not? And then Microsoft is actually new to the game. They have something called the Planetary Computer, which is aimed at giving Google Earth Engine a run of its own. That actually was founded by a fellow named Lucas Jopa, well, he was the spearhead of it, who was a PhD student who graduated from the Nicholas School just a few years ago.